Let's begin. Welcome again. Hope you had a happy, good Independence Day break, doing a lot of homework and project and stuff. It's good to be back though. Today, I'm hoping we can finish with the Iterative Solvers lecture and do some coding together. The purpose is to look a little bit deeper into the theory of iterative methods. And again, this is just scratching the surface. You need significant knowledge of linear algebra to understand linear solvers. We're not going to do that here, but we'll give you a flavor of that. Eventually, the goal is to get to some of the faster and more robust and powerful iterative solvers for CFD, so we can do the driven cavity problem or project 2 with channel flow and other things. We don't have to worry about performance of the pressure solver. And you already have the slicing sorted out in your codes for the finite volume code. So that should have added probably 10 times speed up overall, but the for loop itself, comparison with the for loop, you should have seen like on the orders of 50 to 100x speed ups by moving to slicing. The last piece of the puzzle is going to be replacing our Gauss-Seidel iterative solver or SOR with something more sophisticated and faster. That will be part of your next homework. You're going to put that in the code, and you will have a fully complete code ready to tackle on other problems. To conclude this lecture, we left off here this time. We said we're going to use the framework that we discussed earlier with this iterative method general explanation. There was this matrix here, I minus P inverse A. A is the coefficient matrix for the original system of equations that you're solving. So for example, if you're doing a Poisson equation, this A would represent the discretization of the Laplacian operator. P is the preconditioner. The inverse P is the inverse of the preconditioner. Preconditioner is a matrix that looks like, that approximates A, but that's much easier to invert. I identity matrix. We call this I minus P inverse A. We call that the iteration matrix, M. And our iterative method looks like this with an iteration counter K. So the new iteration value is M UK. UK is the kth iteration, plus P inverse B. That was the general framework we used for setting up iterative methods in general, or what we call stationary iterative methods. There's something else called non-stationary methods. We'll cover that once we're done with these slides here. A, our coefficient matrix, can also be decomposed into a lower diagonal plus main diagonal plus upper diagonal matrices. That's going to come in handy. Now we're going to apply this to the Jacobi and Gauss-Seidel and SOR. And my objective here is to try to close the loop into what we demonstrated last time in class, that Gauss-Seidel was pretty much twice as fast as Jacobi for this problem. And SOR had a range of performance, as you've shown also in your homework assignments, based on that relaxation parameter, beta or omega, whatever you called it. Okay, so I'm going to try to use this framework to explain how those three methods work. I'll start with Jacobi. I explained this quickly last time. This was the general method for the Jacobi solver. And we simplified it a little bit by combining those two terms here. So that gives you the standard Jacobi, except this summation here is done for all off-diagonal items. If j equal I, that means this is a main diagonal entry. For j different than I, it means all the off-diagonal entries. That's how you would think about it. Now, my objective is to convert the Jacobi into this iteration matrix form. And you will notice that this 1 over AII is simply the inverse of the main diagonal. BI is the right-hand side vector. This one, I split the summation into the lower diagonal, the lower triangular matrix, and the upper triangular matrix. So this entire summation, sum Aij phi j, for j less than I, that only means this is simply the lower diagonal, the lower triangular matrix, the product of the lower triangular matrix with the solution vector at the kth iteration. So L phi, and then same here, this is U phi, where U is the upper triangular matrix. If you do this, then you can write the entire Jacobi method as matrix vector products, and that gives us automatically that formulation that we set out with the M matrix and so on and so forth. So it gives you minus D inverse L plus U phi K. So that would be our M matrix, and D inverse B. So that tell you this is D is the preconditioner. In other words, so there's another way of saying it. For Jacobi, we choose the preconditioner to be D, and then we use our formula as such, I minus, remember we had a P inverse here, so that would be D inverse and D inverse B. So that's coming from the standard formula, which is up there. That was our standard iterative formula. You can come up with your own by choosing whatever P you like. Now you split A into lower, upper, and main diagonal, and you simplify a little bit, right? Because A becomes L plus D plus U, D inverse D becomes I. You rearrange things, and you get this. This is our iteration matrix, as we've demonstrated also in the previous slide. Now, for the Laplace equation, when you discretize it using central differencing, that gives you values for the main diagonal, for the lower and the upper triangular matrices, right? So those are generic until you choose a problem. When we choose the units, the Laplace equation on the unit square, or the Poisson equation on the unit square, it determines what those are. And remember, for our general iterative methods theory, the spectral radius of the iteration matrix needs to be less than 1 for the method to converge. Okay? If you've reviewed the slides, that M matrix, this matrix, the eigenvalues of this matrix are critical in making sure that the method is convergent. And the worst eigenvalue, which is the spectral radius, the largest eigenvalue in magnitude, is going to determine if you're going to converge or not and how fast you're going to converge. The smaller the spectral radius, the faster you're going to converge. If the spectral radius is close to 1, your convergence is going to be slow. So let's see what happens. For the Laplace equation on the unit square, it's easy. We can determine the eigenvalues for this M matrix, and you get this spectral radius. That's the maximum eigenvalue for the M matrix, and you get 1 minus 1 over 2 pi squared over n squared, where n is the number of grid points that you have. Okay, so as n approaches infinity, you see, or for even any decent n, right? So this is n squared, n to the fourth. This is very close to 1. The spectral radius of the Jacobi method is very close to 1 for the unit square. Okay, so that at least explains like why that method converges very, very slowly. It's only slightly less than unity for large matrices, hence the slow convergence. Okay, so now we go to Gauss-Seidel. The preconditioner for Gauss-Seidel is the lower triangular matrix and the main diagonal, so L plus D. So you take the main diagonal, everything below it. That's our preconditioner for the Gauss-Seidel. Remember, with the Gauss-Seidel is the same as Jacobi, except we use the most recent values. Okay, so the most recent values will be represented by the lower diagonal, because we're starting at the first equation, we fill in the first point, we go to the second equation, we use that previous point to fill in the second point, and so on. You kind of fill in that solution as you go along. So we do expect, and we've demonstrated that we're going to get better convergence. Let's see how this works out mathematically. Again, you run this through that framework that we have, I minus P inverse A plus P inverse UK plus P inverse B, and P is L plus D. So you put in the matrices over here, you simplify, and you get this. So this would be our M, or iteration matrix, minus L plus D inverse times the upper triangular matrix. And for the Laplace equation on the unit square, so again, when you choose the problem, that gives you the discretization, the coefficient matrix, and U and D and L are from the coefficient matrix. Then you get, for rho Gauss-Seidel, is cosine pi over n squared, which is the square of the Jacobi spectral radius. Okay, we've squared the Jacobi spectral radius. Now, when I show you the remaining math, this too actually tells you you're going to be twice as fast as Jacobi. Okay, twice as fast as Jacobi. So let's see how that works, twice as fast. Remember that for each iteration, the number of exact digits, this was called the rate of convergence, how many exact digits can you add at every iteration, is related to the spectral radius. It's given by minus log 10 times the log 10 of the spectral radius. So now you compare tau gs, the number of digits added by the Gauss-Seidel solver, over tau Jacobi. You get minus log 10 rho GS over minus log 10 rho Jacobi, minus cancel out. You get, but rho Gauss-Seidel is rho squared Jacobi. So you get 2 log rho Jacobi over log rho Jacobi, and you get 2. And therefore, the number of digits in the Gauss-Seidel is 2 times the number of digits of the Jacobi method. So twice in every iteration. So you're going to converge twice as fast. Okay? So that at least explains the observation we saw in class last time, if you remember. Okay. Now on to SOR, which is a little bit harder to look at. The preconditioner for SOR is d over omega. That's the relaxation coefficient. We called it beta or alpha sometimes. I'm going to call it omega here for some reason. So it's d over omega plus the lower triangular matrix. So it's very close to Gauss-Seidel. Remember, Gauss-Seidel was d plus L. This one is d over omega plus L. So we're rescaling those main diagonal coefficients, okay? And then when you run this through the framework, you get this for the M matrix, t plus omega L inverse into 1 minus omega times d minus omega times the upper triangular matrix. Okay. Now, there's a lot of math involved here, and I have a reference for that I will that's already in the files in Canvas. If not, I'll add it this evening. What you get is a relation between the eigenvalues, not the spectral radius yet, the eigenvalues of SOR, called lambda SOR, omega, and the eigenvalues of the Jacobi method. Call them uj, or I could have called them lambda Jacobi. I don't want to put lambda so we don't confuse the two. So you get a relation between the eigenvalues of SOR and eigenvalues of Jacobi. Now, the question is, can we find an optimum omega that will maximize the convergence of SOR? How do we maximize the convergence of SOR? By minimizing the spectral radius of SOR. What is the spectral of SOR? It's maximum lambda SOR. So you need to solve this equation, this quadratic equation, to find the maximum lambda SOR, okay, and make that a minimum, right? Because the spectral radius is maximum lambda, and you want to choose omega so that it minimizes that. It turns out that you can solve this problem entirely, and you can find an optimum omega, and that's equal to 2 over 1 plus the square root of 1 minus the Jacobi spectral radius squared. Okay, so the Jacobi spectral radius was cosine pi over n. Okay, and then you can demonstrate that with the problem you did in class, and you can find omega optimum 1.8 or 1.85, 1.83 based on your number of grid points. It's a miracle. Okay, and this is an exact result. Now, SOR can achieve, like we've shown, significant orders of magnitude in convergence, for convergence. For these, here are some spectral radii of the Jacobi, Gauss-Seidel, and SOR iteration matrices. And you see that you're splitting hairs. For Jacobi, it's very close to 1. As you increase the number of grid points, remember you have cosine pi over n. Okay, and as n approaches infinity, you're going to get almost cosine 0, which is 1. So you're going to start 0.99, 0.997, 0.999, 0.9998, and you're going to get closer to 1 for Jacobi, and convergence is going to be slower and slower and slower and slower. For Gauss-Seidel, again, it's the same story, but it's just barely, the difference is in the second significant figure, right? But that bare difference gives you twice the convergence rate. But then look at SOR for the spectral radius for SOR at the optimum omega. Look at that. You're still matching. You're still at the highest resolution. Your spectral radius is smaller than the best case for Gauss-Seidel in this case. Okay, so it does a good job. We're not going to use SOR. We're going to use even better solvers, okay, and faster solvers. And that leads me to start the discussion on non-stationary iterative methods. And we're not going to go into, there's only a few slides here. I'm not an expert in this area. I did dabble in it a lot during my master's work, but I forgot everything about it. So, I'm just going to present what I remember and some of the theoretical results. So the idea of non-stationary methods is that with Gauss-Seidel, Jacobi, and SOR, the M matrix was a constant. Okay, for every iteration, it was a constant. There are results that we will see in your next homework that have to do with the frequency of the signal in as you approach the solution. We notice that high frequency signals we can converge them faster to a solution because they look like a diffusion process. We can converge them faster to the solution. But once you dissipate them, they slow down. So the idea here is like, well, how about we can change the iteration matrix if we detect that our convergence is slowing down? Let's keep adjusting our iteration matrix so we kept changing that spectral radius per iteration. So you come up with these non-stationary iterative methods where M is a function of the iteration counter. So now iteration matrix depends on the iteration. Typical methods are conjugate gradient by conjugate gradient method, conjugate gradient stabilized, generalized minimum residual, or minimum residual methods. There's a bunch of those. All of those are non-stationary. They generally belong to gradient methods. Okay, now before I explain that procedure, I want to show you how solving a linear system can be thought of as a time integration procedure or a solution in time. So we start with the diffusion equation, simply the Laplace equation del squared u equals 0. Okay, and we know that this solution del squared u equals 0 is the steady state solution of du by dt equal del squared u. Agreed? So at steady state, if you solve this equation to steady state, you're going to recover this. Okay? So now the idea, why not take this equation and solve it in time until steady state? That should give us the solution to this linear system. Okay? Simple, very simple idea. And guess what? If you go and do forward in time and central in space, say a standard finite difference grid. So forward Euler in time, un plus 1 minus un over delta t plus central differencing for del squared u. Okay? And then you rearrange terms. Okay? So you solve for un plus 1 just like we did in the past. So we solved this problem previously and solved it in time. And you rearrange things a little bit. Okay? Then if you choose your maximum time step size from the diffusion stability limit, delta t over h squared is 1 over 4, then what you get is nothing more than the Jacobi iterative method for equal spacing. Okay? So one way to think about this is that iterative methods can also be thought of as time integration methods. And with time integration methods, you can choose different time integrators to accelerate your approach to the solution. And so in a standard method, time integration method, you would probably want to take this path to reach the solution because you're interested in the local dynamics of what's going on in the problem. But if you're only interested in the steady state problem, what you want is to go directly from the initial guess to the steady state solution. Okay? So now I'm going to tie this back into hopefully to the gradient methods. I don't know why I had these slides on, but anyway, so that's one additional thought to think about iterative methods as not necessarily just like their own thing. They could be thought of as time integration methods. And in fact, there's a whole theory called pseudo-transient continuation. They add an artificial time derivative and try to solve a problem to steady state just by solving the time-dependent problem. Because once you introduce time, you have other tools for time integration, Runge-Kutta integrators, implicit integrators, and so on. They're not necessarily faster than some of the traditional methods, but in some cases they are. Anyway, so now we talk about gradient methods. Gradient methods are the standard class of methods for non-stationary iterative methods. However, they only work for symmetric, positive, definite systems. And for those systems, A is equal to its transpose, and you have to satisfy that phi transpose A phi is always positive. Okay? So that's an always positive quantity. Now, you reformulate the problem as a minimization of the quadratic vector. Now, where does this come from? It comes from like regression analysis and kind of matrix linear system theory. But bear with me for a second. If we define this quantity, this is a quadratic quantity because when you see phi transpose phi and phi, this looks like phi squared, phi, and a constant. So this quadratic vector is 1 over 2 phi transpose a phi minus b transpose phi plus c. Bear with me for a second, because the solution of this, the minimization of this quadratic, is the solution to the linear system. Now, Q is a minimum if its gradient with respect to phi is 0. So this quantity is a minimum if its derivative, Q prime with respect to phi, is equal to 0, right? Now, why this is a minimum? Because this would satisfy the second derivative test. When you think about regression analysis, why does minimizing the sum of the residuals always gives you a minimum? Because of the properties of the system. The second derivative test always determines that this is a minimum, not a maximum. Remember, the condition that a derivative is equal to 0 gives you an extremum. You can't tell if it's a minimum or a maximum unless you do the second derivative test. So you make sure that it is a minimum or a maximum. In this case, because this has these properties, this is always minimizing this, or setting Q prime equal to 0 is always going to give you a minimum. Now, what is Q prime? Simply the derivative of this with respect to phi. So you get 1 over 2 a transpose phi plus 1 over 2 a phi minus b. OK. So now listen, check this out. Q prime is this. Now, A is symmetric, so A is equal to A transpose. So if A is equal to A transpose, then those two give you A phi minus B. So the minimum is obtained when the gradient of Q is 0. And if the gradient of Q is 0, then this implies that A phi equals to B. So instead of going after A phi equal to B, we go after minimizing that quadratic vector. Because if we minimize the quadratic vector, we are solving Q prime equals 0, which implies, by definition, that A phi is equal to B. So we don't go after A phi equal B. We go after Q prime of phi, minimizing Q. Okay? And that gives the idea of these gradient methods. OK, so 1 second here. Yep, that's it about that. Okay? Now, this gives rise to conjugate gradient method by conjugate gradient. When you think about gradient methods, they're essentially they're doing like search in the vector space to find the minimum of Q. That's what they're doing, all of those methods. Conjugate gradient by conjugate gradient stabilized, minimize residuals. They're all different ways of finding that minimum of the quadratic vector of Q. That's it. That's what they're doing. So instead of solving the system of equations A phi equal B, we find the minimum of the Q vector, which for some reason is easier. Okay? Anyway, so now it's time to get our hands dirty with some advanced sparse solvers. We're going to do some work, some coding in class, and then you'll take it on in your homework assignment, because I want you to put one of these solvers or all of them into your finite volume code. Okay? All you need, it turns out, is the coefficient matrix and the right-hand side. And the rest is easy. You just make a call to a solver. So there's a whole class of sparse solvers in Python. There's only one direct sparse solver. Now, remember the theory of linear solvers. We have direct and iterative. Direct solvers are expensive. They solve the system exactly. For sparse methods, for sparse systems, this is not recommended, except for one called the sparse solver provided in Python. It's called spsolve. It comes with lin algebra package. But it's from SciPy, not NumPy. So the spsolve function in the SciPy sparse lin algebra module, it's a direct solver for sparse linear systems. So a direct solver is going to give you what? An exact solution. Okay? So there's no concept of tolerance over there. You don't pass a tolerance to the sparse solver, spsolve, because it's to the direct solver. It's a direct solver. It's pretty fast compared to the standard dense solver that we've used, numpy.linalgebra.solve. And it's specifically dedicated for sparse systems. So that means you have to give it a sparse matrix. Okay, you have to give it a sparse matrix. It's optimized for sparse linear systems. It uses LU decomposition. It's efficient, suitable for problems where iterative solvers might struggle, which we're not in that category. So, but we still use it. We use it in some of our research because it gives us 0 error in our pressure solve, and it works really well for relatively small number of grid points, like 64 squared or even 128 squared. That's kind of what our data shows. The function supports various sparse matrix formats. We're not going to worry about that. We're only going to use compressed row storage for this. It's pretty efficient. And anyway, so that's SPSolve. That's one of the solvers we're going to use. Now, that's the only direct solver that I will endorse for sparse systems. Okay, you want to use it? Great, that's fine. Eventually, I recommend you all use the algebraic multigrid solver, which is at the end of these slides. Okay. Now, there's a whole category and library of iterative solvers for sparse systems. Remember, we are within sparse systems. There's a lot of discussion here on SciPy, sparse linear algebra, so you can follow that link and see a bunch of things over there. Some of the common solvers, like I said, well, SPSolve, it's direct, conjugate gradient, biconjugate gradient stabilized, GMRes, generalized minimum residual, LGMRes, MinRes, a bunch of things. Probably the fastest solver is going to be the algebraic multigrid. And we will use the PyAMG implementation. That's why I sent the announcement earlier today for you to install PyAMG. And you can use pip or conda install PyAMG. Okay. Now, this is a list of the solvers taken straight out of the SciPy page. And here I have an explanation for them. So conjugate gradient methods, they're best for symmetric positive definite systems. And it's efficient for large symmetric positive definite systems, which is the case we're dealing with. Structured uniform grids. For the pressure, we have an SPD, large SPD matrix, so it works great. GMRes is for non-symmetric and non-positive definite systems. You know, it will work for us, but it's not necessarily the optimal one. Biconjugate gradient works better for non-symmetric systems, and it's an extension of the conjugate gradient method, but it goes in two directions. And biconjugate gradient stabilized, apparently this method becomes unstable for some systems. And so this one is a little bit more stable to converge. And then conjugate gradient squared, there's like three or more. What we're going to use from this is just this one, the conjugate gradient method. And here I give a simple example of just using solving a one-dimensional heat equation. And we discussed this already, the sparse diagonals, in one of the slides. We're going to implement this together on a two-dimensional problem. So don't worry about that. And then you simply call SciPy sparse linear algebra, and you call the solver. You give it the coefficient matrix, you give it the right-hand side, and you give it a tolerance. Couldn't be easier than that. Now, these methods, because they're iterative, they need a tolerance, okay? So you're going to need to provide a tolerance. In your homework, when you're comparing this to SOR or Gauss-Seidel, make sure you set the same tolerance on both solvers, okay? Yeah?
I have a quick question about your choices of tolerance. So you said in the last lecture that the tolerance that you choose basically declares how many correct significant figures there are
Yeah.
in our solution. So when you say correct significant figures, I guess it depends on maybe the system we're trying to solve, like how accurate do we need to be, or?
Yeah. So the one other way to think about it, this is a great question. It's always like, oh man, what do we, how do we pick our tolerance? Let's take the pressure solver, okay? And the pressure solver is directly tied in, the Poisson equation for the pressure is directly tied into the dilatation. So our objective is to drive the dilatation to 0, period. Div u equals 0 at every point. So the tolerance in that sense, when you set a tolerance of 10 to the minus 9 or 10 to the minus 15 or 0.1, right? That is going to be the value of your dilatation, right? So as you iterate more, or when you set your lower tolerance, you're going to get more and more and more close to that target value. Remember, in your system of equations, you know your target, A phi equal B. So how close do you want A phi to be equal to B, right? So the difference between A phi and B, that is going to be your tolerance. That's going to define your tolerance. Now, most of these solvers will use either a relative error between iteration k plus 1, iteration k, or they would use A phi minus B over B, okay, as a relative measure of the magnitude of the system. Either way, for these systems we're solving, they will get you the answer that you're looking for. And when you think about the pressure, this is exactly what we want for the pressure solver. Yeah.
So the
No, this is a norm. This tolerance is a norm of the total error in your entire system. It's typically the worst, either in L2. You can check the function and check the API and see what tolerance they're using. Typically, they use an L2 norm on A phi minus B over B, a relative measure, but it doesn't depend on your grid resolution. Your tolerance is fixed regardless of the problem size.
No, I mean, doesn't it depend on the machine that you are solving the problem on?
On the machine you're solving the, oh, I thought the meshing, sorry. Not at the, I wouldn't worry about that. I wouldn't worry about that. No, it doesn't. It will continue working until you get to that point. Okay, it might get there sooner or faster. That depends on your, your specific setup. But once you get a solution with an error like that, it's going to be comparable to his and theirs, right? So it's not going to be an issue there. I wouldn't worry about that. Okay. PyAMG is the Python algebraic multigrid solver. I'm not going to cover multigrid this year. I think it's beyond what I want to do this year. But the idea of the algebraic multigrid is that, and we will see some of these ideas in the coming lectures. We saw some of those ideas earlier on when we looked at diffusion. We noticed that high frequency signals dissipate faster than low frequency signals. It turns out with iterative solvers, you see the same thing. High frequency errors or high frequency signals in the solution process, they converge faster to the solution than low frequency ones, okay? And you will demonstrate this with the Jacobi method in your next homework. We will take a problem, a simple diffusion problem, and we will put a signal on the right-hand side, like sine pi, sine 2 pi, sine 4 pi, sine 16 pi, and you will notice that the number of iterations on the higher frequency is less than that of the lower frequency. Right? So that seems to be a property of all of these solvers. The idea of PyAMG is, so remember, when we're talking about the time complexity for these algorithms is, how can we converge faster? How can we make the convergence go faster? We can mess with the spectral radius of that matrix, or we can make the signal, the problem itself, just converge faster. So even for that same spectral radius. The idea of AMG is that a signal, a low frequency signal on a fine grid will look as a high frequency signal on a coarse grid. A low frequency signal on a high resolution grid is going to look as a high frequency signal on a lower resolution grid, on a coarser grid. Why? Because there's bigger change. So if you had 100 points and you switch them to 50 points and you keep that same signal, when you go from one point to another, you're going to see bigger change in the value. If you go to 25 points, you're going to see even bigger change in the value. So you've changed the frequency of the data, the sampling frequency if you want. So that's the idea of multigrid. That's geometric multigrid. Algebraic multigrid is similar. But the idea is once we feel that our solver is not converging anymore, once we detect that our solver has slow convergence, we switch to a coarser grid. What that does, it takes because we've dissipated all the high frequency errors in our solution. We've converged them. Now we take those and move them to a coarser grid. We interpolate them, approximate them. On the coarser grid, they're going to look like high frequency errors. So their convergence rate is going to be higher. We solve them on the coarser grid. And once we no longer converge fast, then we go on and keep going on. Has anyone heard of the V cycle, W cycle, F cycle for multigrid? You've heard of that. Okay. So the idea with multigrid, okay, I'm going to have a whole theory of multigrids here, how it works. Okay. So the idea is, this will be an option for us when we use PyAMG. The idea is you start with your fine grid, you coarsen, and then you refine, and each step you are solving the system. Or you can have a W cycle. Some of them have an F cycle, goes like this, okay? And you have many levels here. You could have 15 levels or 3 levels. That will be an option when we use the PyAMG solver. Does it matter much, these cycles, how many refinements, how many coarsening you do? Not much. I always use the V cycle and call it a day for the problems we're dealing with. But that's as far as you're going to be involved with algebraic, with multigrid. If you want more, I can send you a great textbook on multigrid. But multigrid is one of the best iterative solvers and one of the fastest iterative solvers that we can use these days. Okay, so the PyIMG, Python Algebraic Multigrid, is designed for solving large sparse systems, obviously. The PyIMG provides many solvers. We're not going to use all of them. We're only going to focus on one type of solver, okay? But I'm putting this for completeness in case you might need to use it for something else in your research. So PyIMG provides a multigrid solver and a bunch of Krylov solvers. So generalized minimum residual, conjugate gradient, etc. So those non-stationary methods. Well, we already have SciPy for non-stationary methods. We're not going to use this. We're going to focus on the multigrid. And it also provides preconditioners, algebraic multigrid preconditioner, smoothed aggregation, SAAMG. So it gets really fancy. So these are preconditioning techniques that you can use with these methods. So you can leverage PyAMG to create a preconditioner that you can use with the conjugate gradient method from SciPy. You can mix and match. Anyway, we're not going to worry about this. All we're going to need is this multigrid solver. Okay. Now, the option that we will use is called the Rook-Steuben AMG solver. So that's the only solver we are going to be using for the pressure, okay, for moving on. And the way you call it, you say PyIMG dot Rook-Steuben solver, and you give it the coefficient matrix. We will see how that works. This is a classic algebraic multigrid solver, and it has a bunch of options. Maximum level, so this is in the V cycle, how many levels do you want to go? 5, 6, 10, or 4 levels, okay? And you can choose the cycle that you want, V, W, or F cycle. How many, what is the maximum size of the coarse grid? We're not gonna touch that. The method of strong connection in the you're even not gonna touch that because this gets deeper into the weeds of multigrid theory, okay? And that's a course by itself. But what I want you to know at least is that this multigrid works, and roughly it operates by accelerating the convergence of the solver by changing the frequency of the error by either changing the grid or changing the matrix coefficients. The algebra, what I described earlier by putting more grid points, is called geometric multigrid. That's not always possible for unstructured grids, for example. How do you combine elements together? The algebraic multigrid doesn't do it on the geometry. It does it on the coefficient matrix. So it takes blocks of the coefficient matrix and averages them together to mimic that effect of changing the frequency of the error. Okay. Again, it's way more complicated than what I'm describing here. Okay. So you always start with the Rook-Steuben solver for these classical problems. For more complex systems, you use the smoothed aggregation solver. We've never had to use that. Experiment with different parameters like multigrid cycles, strength, or smoothing. You know, it's up to you. Play with them. And you can use it as a preconditioner, like I said. It is pretty robust. PyAMG, according to the plot that I showed you a long time ago, PyAMG gives you the most stable and reliable timing for these problems. So if you look at the cost of all of the solvers, dense direct solver, conjugate gradient, sparse, SP-solve, and multigrid. Multigrid is nearly fixed, has a fixed time complexity. It stays flat regardless of your grid resolution. So it's a very robust problem, very robust solver. However, for your projects or homework, you're going to be operating maybe at 64 grid points or 128 grid points. You should be okay using either the conjugate gradient in orange or the SP-solve or the algebraic multigrid. But for your research, you're probably going to, maybe you're doing something in turbines, you want to go to 512. What do you use? You use the algebraic multigrid solver, okay? It has a fixed time complexity. Okay, what I'm going to do with the remaining time is I'm actually going to solve this same problem, del squared U equals a bunch of random numbers in the domain, and they're going to diffuse to like a blob, essentially. You're going to put just random numbers on the right-hand side on an n by n grid, on a finite difference grid. Okay, so I don't want to involve finite volume. There's walls everywhere, and U is 0 everywhere on the wall. So very simple. But we're going to focus now on using that sparse coefficient matrix. I had that in one of the slides earlier, and that should probably just send that out to you. So if you remember this, so we're going to be using this approach to create the sparse diagonals, and then we're going to pass this coefficient matrix to these different solvers. Okay, then it will be your job to take this and put it in your CFD code, in the finite volume code that we have. Okay, so let's grab our Jupyter notebooks.